We have been practicing finding all possible solutions to trigonometric equations. However, it's not always necessary to find every solution to trigonometric equations. Sometimes we only need to find solutions within an interval, and that's what we're going to practice in 4.2.3. Let's see how this works out on example 6. Solve the following equations in the given interval. So on question A, we have 3 cosine of alpha plus square root of 12 equals 5 cosine of alpha plus the square root of 3. But we only want the solutions for alpha between negative 360 degrees and 360 degrees. We'll start the process in the same way. Remember, our first goal is to isolate that cosine function. So I'm going to combine both of our cosine of alpha terms on one side by subtracting 5 cosine of alpha from both sides. In addition, I'm going to combine all of our constants on one side by subtracting the square root of 12 from both sides. On the left side, you can see we have negative 2 cosine of alpha. And on the right side, we have square root of 3 minus the square root of 12. Now, think about 12 as 4 times 3. Then the square root of 12 would be the square root of 4 times the square root of 3, or 2 square root of 3. So we can simplify the right side by combining like radicals. We have negative 2 cosine of alpha equals negative square root of 3. 1 square root of 3 minus 2 square root of 3 gives us negative 1 square root of 3. Continuing to isolate our cosine function, we can divide both sides by negative 2, and we end up with cosine of alpha equals square root of 3 over 2. So we need to find alpha as the inverse cosine of square root of 3 over 2. Taking a look at the interval over which we're solving this equation, we can determine that we're working in degrees. This means we need to find all of the angles between negative 360 degrees and 360 degrees with a cosine value of square root of 3 over 2. So once again, our unit circle will be helpful. First, note that cosine of 30 degrees gives us square root of 3 over 2. In addition, cosine is positive in quadrant 4, so we know this angle, which we could view as either negative 30 degrees or 330 degrees, would be the first two solutions in the unit circle for our given trig equation. If we were finding all solutions to this trig equation, we would simply include those two angles plus any multiple of 360 degrees to consider all other angles coterminal with those two given angles. However, we only want to list the solutions in the interval from negative 360 degrees to 360 degrees. Well, we have two solutions between 0 and 360. Let's look at one negative rotation around the unit circle. If we're rotating in the negative direction, notice this angle could also be written as negative 30 degrees, and this angle could be written as negative 330 degrees. This means we have 4 total solutions in our solution set. I'm going to write this in set notation and simply separate each individual solution with commas. Because we're working in degrees, it's also important that each angle does include that degree symbol. So our 4 solutions are negative 330 degrees, negative 30 degrees, positive 30 degrees, and 330 degrees. So there's 4 solutions of this equation on the 2 given rotations around the unit circle. This is what it means to find all solutions within a given interval. Let's try an example in radians. In example B, we have the equation 1 equals 2 sine of x. As always, our first goal is to isolate the trig function. Dividing both sides by 2, we can see that 1/2 equals sine of x. Then we can isolate the argument by applying the inverse sign to both sides. So we need to calculate inverse sine of 1/2 to get the solution x. Observing from the given interval, it's obvious that we should be working in radians. So we need to find all possible angles between negative pi over 2 and pi over 2 with a sine or a y-coordinate on the unit circle of 1/2. Note that for pi over 6, sine of pi over 6 is equal to 1/2. Now, according to the given interval, we're looking for all of the angles between negative pi over 2, and pi over 2. Because sine is only positive in quadrant 1 of that interval, we have found the one and only solution of that trig equation on the interval. So the solution to this equation is singular. We end up with the angle pi over 6. The overall process is the same as that in the previous videos that we've studied. The only difference is that instead of listing every angle coterminal with our given solutions, we only list the solutions that belong to the stated interval. Don't forget, you can always check your solutions with your calculator. The ability to solve a trigonometric equation in a given interval will be useful in courses such as calculus, but also in physics. Let's look at an application here in example 7. Example 7 deals with Snell's law, which governs the physics for light moving from one medium to another. Snell's law states that the ratio of the sines of the angles of incidence and refraction is equivalent to the ratio of its phase velocities in two media, v1 and v2, or equivalent to the reciprocal of the ratio of the indices of refraction, n1 and n2. Okay, did you get all that? Let's pause and make sure we understand what's being referred to there. The angle of incidence, let's suppose we have a ray of light that's moving from one medium. That first medium is above that horizontal x-axis. Its angle of incidence is known as theta 1. As it moves from one medium into another, such as from air to water, that light wave changes the angle. This angle here, theta 2, is known as the angle of refraction. Now, the velocity of light in air versus the velocity of light in a medium such as water is different. So one way to express Snell's law is to say that sine of the angle of incidence, theta 1, divided by sine of the angle of refraction, theta 2, is equal to the ratio of the phase velocities. We call that v1 and v2. So this is one expression of Snell's law. Another way to write Snell's law is to take this ratio of sines, that is sine of theta 1 divided by sine of theta 2, and set it equal to the reciprocal of the ratios of the indices of refraction. So we're going to find the ratio of the indices of refraction and then reciprocate it. So instead of n1 over n2, we have n2 divided by n1. For this particular problem, let's consider a ray of light as it changes from moving in air to moving in water. So let's suppose that the medium above the x-axis is air and the medium below is water. So as light waves hit water, the direction of the ray changes according to Snell's law. Let's find the angle of refraction, theta 2. Now theta 2 is going to be between 0 and pi over 2. If I'm thinking in degrees, that's between 0 degrees and 90 degrees. If theta 1, the angle of incidence, is pi over 3, so we're looking at this being pi over 3, also known as 60 degrees. N sub 1 is 1.00, so we're looking at air above this line, and the index of refraction for water is 1.333. These are known measured values. So we want to find the angle of refraction. Therefore, we can use Snell's law as it's stated with the indices of refraction as sine of theta 1, that's given to be pi over 3, divided by sine of theta 2, that's unknown. We're going to solve for that. This is going to be equal to n sub 2, that's 1.333, divided by n sub 1, 1.000. I'm going to start by cross-multiplying. 1 times sine of pi over 3 is square root of 3 over 2. And over here we have 1.333 sine of theta 2. So again, I'm cross-multiplying and I evaluated sine of pi over 3. To solve for sine of theta sub 2, we're going to divide both sides by 1.333. So I'm going to attach it to the denominator here and call it 2 times 1.333 in the denominator, and that's equal to sine of theta sub 2. Now, I'm not going to type that into my calculator until the very last step. I don't want to round 2 times in a row because then I start to build up rounding error. So I'm going to evaluate this once with the calculator. Rounding once decreases our rounding error. So we're applying inverse sine to both sides. And we're going to evaluate this as inverse sine of square root of 3 divided by 2 times 1.333. And that's going to give us the angle of refraction, theta sub 2, and we're working in radians here. So first check to be sure that your calculator is in radian mode, and then we're going to evaluate inverse sine of the square root of 3 divided by, now we got to be careful here because I have an operation going on in the denominator. So I need to group that in a set of parentheses in order to get my calculator to recognize that both of those factors are part of the denominator. So I'm going to close those parentheses, close the argument of sine, and we'll round to the nearest, let's go 3 decimal places. Theta sub 2 is approximately 0.707. And again, that's in radians. So we have answered the question correctly, but I'm kind of curious. If the angle of incidence is 60 degrees, what is the angle of refraction in degrees? So I'm going to convert that radian measure to degrees by multiplying by 180 divided by pi. So in degrees, this is about 40.5 degrees. So if the angle of incidence is 60 degrees, then the angle of refraction here is approximately 41 degrees. So you can see how that angle changes as light passes from air to water. So think of trigonometry when you see Snell's law popping up in your physics classes. Let's look at another application. We're going to see a direct application of our skills of solving trigonometric equation coming up in Chapter 5 very soon. So example 8 says, to determine the measure of angle beta in the triangle below, we can apply the law of cosines. Now, we haven't learned the law of cosines yet. This is coming in section 5.2. But the equation solving skills that we're learning here in Chapter 4 will still be necessary in Chapter 5. So we're preparing for what's to come here. So applying the law of cosines to this triangle, which we'll learn at a future date, we will obtain the equation 10.3 squared equals 5.2 squared plus 6.1 squared minus 2 times 5.2 times 6.1 cosine of beta. So we'll learn how to set that up soon, and I know you're looking forward to that. For now, we simply want to solve the equation for beta between 0 and 90 degrees. Notice you can understand why we're solving this equation on an interval. We're looking for an angle of a triangle, which will be between 0 and 90 degrees. As usual, our first step in solving a trigonometric equation is to isolate the trigonometric function, and I'm going to postpone the calculations until the very last step. So this may look a little bit cumbersome, but I'm just going to manipulate the constants as they are. So the first thing I'm going to do is subtract these two constants from both sides. So we have 10.3 squared minus 5.2 squared minus 6.1 squared. On the other side, this leaves behind negative 2 times 5.2 times 6.1 cosine of beta. Then we can divide both sides by the coefficient of cosine of beta, negative 2 times 5.2 times 6.1. And that will isolate our trig function. So I'm going to make sure and carry that out on this side as well. When we have our cosine function isolated, we can then solve for beta by applying the inverse cosine to both sides. We end up with inverse cosine of 10.3 squared minus 5.2 squared minus 6.1 squared, all divided by negative 2 times 5.2 times 6.1. 6.1 is the constant there. And this gives us angle beta. Again, I'm going to type this into the calculator all in one step. This just requires one calculation, but I have to make sure and keep the operation in the numerator together in a set of parentheses and the operation in the denominator together in a set of parentheses. And instead of using these additional parentheses in the bottom, I'm just going to insert the multiplication operator between those two. Now, don't forget, we're looking for an angle in degrees. So let's begin by switching our calculator over to degree mode. Here we go. Inverse cosine. Open up parentheses for your numerator. We have 10.3 squared minus 5.2 squared minus 6.1 squared. Okay, close the numerator. Enter divided by for the fraction bar. Open a set of parentheses for the denominator. And we have negative 2 times 5.2 times 6.1. So close the denominator and close the argument of the inverse cosine. And we end up with angle beta equals 131.3 degrees. So 131.3 degrees is our solution for beta. So notice we do have an obtuse triangle here. This is just my mistake. We need to be solving for beta between 0 degrees and 180 degrees. That's the only possible solution for an obtuse triangle like that. So that was my mistake. Sorry about that. Make that correction and we have our solution, 131.3 degrees. There's no other angle that I need to look for on the unit circle in order to solve this particular problem, because another angle would be too large of an angle to fit on the triangle. So now you know how to find all of the solutions to a trigonometric equation, and you know how to find solutions within a given interval. A couple of places you may run into actually executing those equations would be in a physics class when you're studying Snell's law, or later in this class when we're studying the law of cosines.